Then it's 11:30 a.m. Norwegian time, and I have the pleasure of welcoming you to the Norwegian Society of Maintenance's meeting with RCM-guru Nancy Regan. I ask all, except Nancy Regan, of course, and Sverre Aastorp, to please turn off your cameras and microphones. My name is Siri Ulvin, and I am the head of administration at NFV. NFV is the organization for companies, organizations, and individuals within the subjects industrial maintenance, production processes, and risk management. We offer a number of courses and conferences within our subjects, both world-class maintenance and many shorter courses. Go to nfv.no for more information. We are very happy that so many are participating here today. This meeting is being recorded, and the recording will be published on nfv.no. Now I leave the floor to Mr. Sverre Iver Aastorp, who is a member of NFV's board and a member of NFV's group for member activities.
Thank you, Siri, and good morning, everybody, and Nancy in special. My name, as you said, is Sverre Aastorp. I am head of maintenance in Statnett, the Norwegian TSO, transmission system operator, and a board member in Norwegian Maintenance Association, as Siri mentioned. For me as a maintenance manager, it is essential to be sure that Statnett does the right maintenance on our equipment, but it's also critical for me to understand the equipment context, working environment, and a whole lot of other things regarding the equipment. Statnett uses RCM to understand the equipment and develop our maintenance strategies. After working with maintenance for approximately 30 years, I have met a lot of people from all over the globe and seen several methods to develop maintenance strategies. I met Nancy for the first time a few years back, and before Corona, we met 3-4 times in person. Nancy is a true RCM believer and has a very nice and easy to understand approach to RCM. She studied RCM with the late John Moubrey and has now her own RCM Academy. She does online training. She has written a book, and that is very good to use both for starters and people that have been working with RCM for a while. And she is very active on LinkedIn. She operationalizes RCM and uses the principles for much more than just maintenance. I hope her RCM pitch today will give you some understanding of the method, and for those of you who are fluent in the RCM, some motivation to keep up the good work. It is a real privilege for me to introduce Nancy to our group and this first meeting this autumn. Nancy, welcome, and just start your presentation. Thank you.
Excellent. Thank you so much. And just one final check just to make sure you can hear me. Is that you can?
We hear you.
Excellent. Well, good day, everyone. I am delighted to have this opportunity to talk about reliability-centered maintenance with you today. Reliability-centered maintenance stole my technical heart over 20 years ago, and I love sharing the technology because I have seen the overwhelming positive results that can be reaped when the process is applied correctly with the right people. So today I want to share about RCM and talk about how it can help you take control of your equipment, but not just your equipment. When RCM is done the right way with the right people, it also helps us to empower our organization and empower our teams. So let's first start by talking about reliability. Reliability is designed, but reliability is designed both literally and figuratively. Now, if we consider it from a literal perspective, the kind of reliability we get from a piece of equipment is largely dictated by the design of the equipment. It's inherent reliability. It is what it is. In other words, you can't get anything more out of a machine than it was designed to do. But we also, as responsible custodians, we also design the kind of reliability we get from our equipment. In other words, we are responsible for the kind of reliability that we get. See, inherent reliability doesn't mean how long something will last without failing. Inherent reliability means how long something will last when it's protected by the right proactive maintenance, but also some other actions that we take. Now, the quality of these actions are determined by our choices, and our choices are governed by our philosophy. And that is the easiest way to explain what reliability-centered maintenance is. Reliability-centered maintenance is a philosophy. And RCM principles were first created out of a real sense of need, because RCM principles first started in the commercial airline industry. Now, at the time, they were having some issues, and that's what gave rise to reliability-centered maintenance. So I would like to share that story with you. Now, the story takes us back to the mid-1950s in the commercial airline industry, where at the time, this is the way that they believed equipment failure behaved. So you see here we have the x-axis with it, which is age, and that can be considered in any number of units. It could be operating hours, it could be calendar time, miles, takeoffs and landings, any number of units. And then you see the y-axis, which is the conditional probability of failure. So essentially what we see here is that the difference between conditional probability of failure and probability of failure is this, is that on the condition, for example, that an item makes it to this area, let's just say this is 1,000 operating hours, for example, on the condition that it survives to that age, now the probability of failure starts to drastically increase. An easy way to express this curve is that things fail because they get old. And this was their philosophy at that time. And that philosophy was reflected in their maintenance plans at the time. They were very high in scheduled overhauls and very high in scheduled replacement. In fact, 85% of components were scheduled for overhaul or replacement at that time. But now time marches on, and now we find ourselves in the early 1960s, and we see the emergence of new aircraft with new systems. We see the emergence of electronics, hydraulics, electronics, pneumatics, pressurized cabins, turboprop engines. So there's a lot of brand new complex equipment, but yet they have to make a maintenance plan for it. So they don't have any practical experience, they don't have any historical data, but yet they have to maintain the equipment. So what they did is they took their existing maintenance plans and they mirrored it to the old ones. And in the case where they had nothing to mirror, they took their best educated guess based upon their philosophy. They put the maintenance plans into service, and the crash rate started to increase. Now, what they noticed is that failure was occurring before that wear out region, before that area where they had anticipated that failure would occur. And the crash rate actually increased to 60 crashes per million takeoffs. So they needed to do something about this, obviously. So based upon their philosophy at the time, what they did is they moved their overhaul and their replacement tasks, and they started to do them more often. So they shortened the intervals. But what happened is the crash rate started to increase even more. Now imagine if you are in charge of this at that time. It was a really alarming situation. So at United Airlines, there were a group of engineers who got together and they said, okay, here's what happened. We shortened the intervals and three things happened. In few cases, things stayed the same. In few cases, things got better. But for the most part, things got worse. And so that's what caused them to step back and say, we need a new way of doing business. And at that time, the engineers there at United Airlines, they got together and they said, okay, we have assumed that, hold on one second, sorry here. We have assumed that equipment failure behaves according to failure pattern B. And they said, okay, we've already challenged that. We've moved the overhaul and the replacement intervals back and things got worse. So they said, let's now challenge the idea that this is the way that equipment failure behaves. So they embarked on an enormous amount of research, and what they found literally rocked the world of maintenance at the time, because what they found is that equipment failure behaves according to 6 failure patterns that you see here. Now, what was most interesting is this. So you see the first 3 failure patterns, they have this age-related phenomena associated with it. But the other 3 failure patterns have this sense of randomness. So you can see here in failure pattern E, which is random failure, there's absolutely no relationship between how old something is and how likely it is to fail. But what was most shocking to them is that when they did their research, and they researched electronics, hydraulics, pneumatics, turboprop engines, and they analyzed structures. And what they found is that only 11% of failure modes were subject to this age-related phenomenon. And what they found is that it was associated with the simple items like tires and brake pads, compressor blades, and aircraft structure. And they proved that actually most failure modes were occurring randomly. And the randomness was associated with complex equipment like electronics, hydraulics, and pneumatics. So they showed that in essence, 89% of failure modes were failing randomly. So they needed a new way of doing business, and that's what gave rise to reliability-centered maintenance. So you see here, if we just take a step back and look for a second, their entire maintenance philosophy was based upon failure pattern B, but only 2% of the failure modes were behaving that way. So that's one of the reasons why the crash rate was increasing. The other thing you can see here is that 68% of the failure modes behaved according to failure pattern F, here where we have this infant mortality, and then it settles down to a low level of random failure. So, you know, infant mortality when things are new and we're working out the bugs, or maybe failure is induced because of maintenance or something is done wrong. So when they were taking care of their equipment, when they believed that it behaved according to failure pattern B, not only were they wasting time, because if most things fail randomly, if you're doing scheduled replacements or scheduled overhauls, it doesn't make any sense, because random means it has the same chance of failing today as it does tomorrow, as it does next week. But they were making things worse because they were reintroducing this infant mortality. So that is how reliability-centered maintenance was born. And it was in the late 70s that the United States Naval Air Systems Command commissioned United Airlines, most notably 2 engineers, Stanley Nolan and Howard Heap, to write a report on how they were coming up with their maintenance plans. And they published the book in 1978, and they called it reliability-centered maintenance. So this is the process now. The definition that I like to use for reliability-centered maintenance is this. It's a zero-based process used to identify the failure management strategies that are required to ensure an asset meets its mission requirements and its operational environment in the most safe and cost-effective manner. Now, one thing to note here is that the definition doesn't say it's a process used to make a maintenance plan, because it does that. But when reliability-centered maintenance is applied correctly with the right people, it can give us so much more. And I will give you some examples as we move on. So the process consists of 7 steps, or answering 7 questions. And the first step is functions. Now, here's what's really unique about functions. my mentor, John Moubrey, this is what he said about reliability. He used to say that reliability isn't a thing on its own, but rather reliability is sprinkled amongst all of the functions of a piece of equipment. So when we identify functions, we're actually defining the kind of reliability that we need from our equipment. Now, too often in our industry, functions are written as a matter of routine, right? You know, to provide compressed air. Well, that's a very general function, say, for example, for a compressor. But when functions are written properly, we write them and we define performance standards for what an organization actually needs. And this can be a remarkable step in the RCM process, because a lot of times when teams sit down and identify exactly what they need from a piece of equipment, one thing that sometimes happens is that they realize the equipment can't do exactly what they need it to do. And that is found sometimes to be a cause of chronic failure. It's such a basic thing that it is often overlooked. Now, step 2 is the identification of functional failures. And then we get to step 3, a really important part in the process, and that is the identification of failure modes. Now, when I use the term failure mode, I'm talking about what specifically causes failure. So I use the terms failure mode and failure cause interchangeably. So no, for purposes of today's presentation, when I say the term failure mode, I mean what specifically causes functional failure. Now, 2 things that John also taught us is that number 1, we manage physical assets at the failure mode level. But number 2, he said that failure modes are the currency of physical assets. Now, if we think, let's just sit back, stand back and think about this from a very simple perspective. So here we've got some American dollars, right? So just like failure modes are the currency of physical asset management, well, money is the currency of us as human beings. So when we look at our currency, we've got, for example, a $1 bill, and in the United States, this will buy you a candy bar. And here you've got a $100 bill, and you know, for about $100, you can maybe buy a new computer screen. So you see, a $1 bill is worth less than a $100 bill, and the same thing goes for our failure modes. You see, if I were to say, let's say I'm walking around the supermarket and I drop these $2 and I lose them, it's not that big of a deal. But if I'm walking around and I lose my $200, that will have a greater impact. It will have far greater consequences. And see, that's why it's so important that we identify failure modes and that we write them properly and include the plausible ones in our analyses. So once we identify failure modes, then we can use the rest of the process to figure out what we should do to manage each failure mode, if anything at all. Step 4 is failure effects. And a failure effect is a little story of what would happen if we did nothing to predict or prevent the failure mode. Now, that's the part that makes reliability-centered maintenance zero-based. So in other words, we do the analysis as if we're not doing any kind of maintenance. And that allows us to sanity check what we're already doing, so we're not biased by our own decisions. Step 5 is failure consequences. Now, here is when we decide how each failure mode matters. For example, could someone be injured or killed? Could we breach an environmental standard, regulation, or law? Maybe it just has an adverse effect on operations, or maybe it has non-operational consequences. Then we get to step 6, and this is when we consider if there's any kind of proactive maintenance that we should be doing, a scheduled restoration, a scheduled discard, or a scheduled replacement task, and if there's any kind of on-condition maintenance that could be done. And a synonym for on-condition maintenance is condition-based maintenance. I think in our industry, the term condition-based maintenance is more widely used, but they mean the same thing. Now, here is where philosophy is really, really important. And it's important for two reasons, because number one, our reliability philosophy has to be rooted in the reality of failure. You know, back in the early days of the commercial airline industry, when they had that complex equipment and they were maintaining it under the assumption that pretty much all failure modes occurred because things got old, well, that's when they got into trouble and the crash rate increased. It's because their philosophy was inconsistent with reality. And still today in our world, still some organizations need to take a look at their philosophy. And most of the basics of maintenance and reliability are embodied in the RCM process. And I want to go over just two parts of the philosophy to give you an example of what I mean when I say RCM is a philosophy. So the first thing I want to share and talk about is preventive maintenance. And we'll talk about scheduled restorations and scheduled replacements. Now, with what I'm about to share, I suspect that there are many of you who are already aware of what I might share. If that is the case, what I would like you to do is think about who in your organization should know about it, but maybe doesn't know about it. Because, you know, reliability has its own language. Just like if I were giving this presentation in Greek and you don't speak Greek, you wouldn't be able to understand me. Well, the same thing goes for our organization, our reliability team members. I know we've all heard that who's responsible for reliability? Well, everyone is, right? It's not just a reliability engineer or just a maintenance manager. It's everyone who has a hand in reliability. So it's really important that everyone speaks the same language. And so this is some of the language I'm talking about. When it comes to a scheduled restoration, or another word for that is an overhaul, or a scheduled replacement task, we know, and we opened the presentation with this is failure pattern B, where the conditional probability of failure increases with age. So as a result, we restore or we replace regardless of the condition at the time. We're not going to go and inspect and only do something if it needs it. We're just going to schedule it and we're going to do it. So the thing about scheduled restoration and replacement tasks is that their intervals are based on the useful life. And that's what we have here. So for example, my 2014 Subaru Forester, the useful life of its engine oil is 7,500 miles. I have it replaced every 7,500 miles. I don't bring it in and ask them to test the oil for me. I bring it in and they change it for me at 7,500 miles because I know if I drive much further, additives will be depleted. You know, water may start to intrude. I'm not going to be able to lubricate my internal engine components properly, and that's just going to cause failure down the line. So it's based on the useful life, not an MTBF, not a mean time between failure, not an average. It's based on a useful life. Now, the next thing I want to talk about is condition-based maintenance. Embodied in condition-based maintenance is more of that reliability language. And again, if you know about this, think about who on your team maybe doesn't, but should. Now, we talked about in the beginning when we talked about the failure patterns that roughly 89% of failure modes in complex equipment fails randomly. But we don't have to be afraid of that, or you know, one could sit back and say, well, what do we do? If it fails randomly, then how can I manage it? Well, the thing is that most failure modes give us a warning that failure is in the process of occurring. In other words, that failure is impending. Now, in the context of reliability-centered maintenance, that warning is called a potential failure condition. Now let's take a look at the P2F curve. Now on this curve, this x-axis is time or age, and again, it can be considered in any number of units: calendar time, operating hours, miles, hours flown, etc. But the y-axis is the resistance to failure. So you see here when, for example, let's just take a new component, the resistance to failure is at its highest. But as time goes by, most failure modes will start to give us a potential failure condition, give us a warning that failure is impending if we don't intervene. And if we don't, then failure occurs. Well, in the context of reliability-centered maintenance, from the time that a potential failure condition is detectable to the point that failure occurs, this is called the P2F interval.
Nancy, do you have time
Yes.
for a question?
Yes, yes, certainly.
Okay. Paul Larry, I'm working for Repsol Oil Company. You said that preventive maintenance only were scheduled restoration and scheduled replacement. As I know the PMs now, they are very often scheduled spot checking without doing anything else. And if I may say, if it's correct, it's a kind of manual CBM. Do you agree?
You mean where they're doing maybe a visual inspection? Do you mean?
Yes.
Yes, that is condition-based maintenance. Absolutely. So they're going and they're looking for a warning sign that failure is impending. Is that what you're saying?
Yeah, that you have some scheduled intervals to check out, and that's most of the PM, at least in the oil industry. You don't do it if everything is okay, but you check something and then you put actions afterwards.
Yes, so you check it and you only do maintenance on evidence of need. Is that correct?
Yep.
Is that what you're doing? Yes, that is on condition maintenance. That's condition-based maintenance. See, CBM can go from continuous monitoring devices installed directly on equipment, something very sophisticated, but it can also be human senses using our sight or our hearing,
Correct.
touch. So yes.
Correct. It's just that when you said preventive maintenance, I agree with you, but I see that what we call PMs nowadays is very often not doing anything directly.
Mm-hmm.
It's done on condition. Okay, thank you.
Yes, okay. And this also brings up another point. In our industry, a lot of people use the term preventive maintenance to encompass everything. In the context of reliability-centered maintenance, preventive maintenance are scheduled restorations and scheduled replacements, and on-condition maintenance is like condition-based maintenance. So all of that is proactive maintenance, but only scheduled replacements and restorations are preventive maintenance in the context of reliability-centered maintenance.
I agree. Thank you.
So let's take a very simple example to illustrate the P2F curve. And let's say we install a new V-belt. Well, we know that after a certain amount of time, how much, for purposes of this example, we don't care. We don't care about this time frame. But once we get to this point where this belt is in the process of failing, it's going to give us some warning signs, right? Visual evidence of cuts or cracks or frays. And if we ignore it, if we don't inspect it and we ignore it, well, eventually the belt is going to break. So from the time that visual evidence of cuts and frays are detectable to the point that the belt breaks, well, let's just say for example purposes that is 6 months. So that's called the P2f interval. But now let's just say that Johnny goes out today to inspect the belt, and he doesn't know where he is on this curve. But let's say Johnny's right here, but he doesn't know it. So he goes out and he inspects the belt, but he does not see any evidence. So now Johnny goes back and he comes back. Let's say he comes back 3 months later. The general rule of thumb with the P2f interval is that you half the P2f interval. So you do inspections at half of what the P2f interval is. But as long as it's less than the P2f interval and you have enough time to act, that's okay. So let's just say, for example purposes, Johnny's doing this every 3 months. So now Johnny comes back 3 months later. He doesn't know where he is on this curve, but he's here. So 3 months later, he detects the visual evidence of where. Well, now we know we have a minimum of 3 months remaining. This is called the net P2f interval, but essentially all you need to know is that what's the minimum amount of time I have remaining to take action to manage the consequences of failure? Well, here in this case, I have 3 months. I have 3 months to do something about it. So let's look at two different scenarios. Let's look at scenario one, and let's say in my operating context, obviously I'm going to have to take this machine offline to inspect the belt. And let's say I take it offline every 6 months. Can this V belt successfully be monitored at intervals less than the P2f interval? And the answer is no, because I stand the chance of missing the failure because my P2f interval is only 6 months. But let's look at scenario two, and let's say my asset is taken offline every month. Can that be monitored at intervals less than the P2f interval? It absolutely can. So when we do condition-based maintenance, we have to make sure that that minimum amount of time that we have remaining is enough time to take action to manage the consequences of failure. Now that might be okay. If I find this warning, I have to replace a pot. Now, what if it takes me 6 months to get a pot? Well, if my P2f interval is 6 months, that's not going to work. But if I have one waiting on the shelf, then it would work. So you see how having this information available to us puts us in a very strong position to make decisions. Now, we talked about philosophy and we talked about the language of reliability. Still today, I talk with people often who, when I share the P2F curve, it's new to a lot of people, but it needs to be this technology, this language of reliability needs to be spread to everyone who's responsible for reliability in an organization. Now, let's talk about a few key points about on-condition task intervals or condition-based maintenance task intervals. Those two terms are synonymous, CBM tasks. I want to talk about 4 key points, three on this slide. Number one, on-condition maintenance task intervals are not based upon MTBF or mean time between failure. MTBF is an average. It's an average that shows about how often something will fail. That's not what we're looking at when we're doing condition-based maintenance. Another thing is that on-condition maintenance intervals are not based on the useful life of a component, and they're not based upon the criticality of the failure. On-condition maintenance task intervals are based upon how quickly failure occurs once the potential failure condition is detectable. And that's the key to condition-based maintenance. The key to CBM, successful CBM, is identifying what the potential failure condition is, defining what failure means to the organization for that particular failure mode, and then defining that P2F interval. Now, that is often not an easy task. And I'm going to share a really good way on how to get those intervals in just a moment. But before I do, I want to talk about shiny object syndrome. I don't know if it's a term here in the United States. I don't know if you use that term in Norway, shiny object syndrome. But this can be a very big issue when it comes to condition-based maintenance. And I talk to a lot of people within organizations where they fall into this trap, meaning organizations often consider advanced monitoring equipment as a solution to reliability problems. You know, like vibration analysis, thermography, sophisticated equipment, continuous monitoring equipment installed directly on equipment. This can be a very expensive trap to fall into if buying and installing the equipment, either installing it directly on the equipment or just buying the advanced monitoring equipment as a first step. And I have an example to share with you what I mean. So my husband is a general surgeon, and he's really big into robotic surgery. So the Da Vinci robot came onto the scene years ago, and it's more widely being used. So essentially, this is the picture of the operating room. This is my husband at the console. So the surgeon is actually not at the side of the table with the patient. The patient is maybe about 4 or 5 feet away, but he's at the console operating. And so these are the arms of the surgical robot. And you can see these are the ports. And it's really amazing what happens with this robot. He specializes in repairing complex hernias. He does what's called abdominal wall reconstruction. Now, this is a hernia. It's really exaggerated. It's a hernia that's about 12 by 24 centimeters. It's exaggerated because when they do robotic or laparoscopic surgery, they insufflate the abdomen with carbon dioxide so that they can see better with the camera and move around with the instruments. But one thing that my husband noted is that the robot doesn't make a mediocre surgeon excellent. The technology is not what makes an excellent operation. See, a surgeon has to have the right prerequisites, the right experience to be able to capitalize on this awesome robotic technology. So a surgeon needs to know how to do this operation open, but before the robotic or the laparoscopic approach, a surgery like this, a person would have like a 6 to 8 inch incision. So the point is that if you've got a not so good surgeon, the robot is not going to make him really great. In some cases, it could make things worse because now he's got the anatomy to deal with as well as figuring out the technology of the robot. Well, see, the same thing applies to our industry. So just like a surgeon has to understand the anatomy and has to be able to do the operation in an open fashion before they move to the robot, when it comes to us with condition-based maintenance, we have to make sure we go about it correctly, right? So there are 2 scenarios. One, where we fall into that expensive trap of buying and installing the monitoring equipment first. But that can be very expensive. The correct way to go about it is, number one, let's define what we even need to achieve with our equipment. That's going back to writing functions. So it's no coincidence that that's the first step in the RCM process. Secondly, we identify the failure modes that we intend to manage, because remember, we manage physical assets at the failure mode level. So then, once we do that, we write our failure effect, we assess the consequences, then we can figure out what potential failure condition we even intend to monitor, and then we can identify the P2f interval and make sure that it's long enough to manage the consequences of failure. So once we do that, we can determine if it's cost effective for us to make that investment when it comes to the sophisticated equipment. Because quantifying potential failure conditions in P2f intervals, in some cases, that can take some time and resources. So we have to sort all that stuff out ahead of time and only implement the technology if it makes sense. See, the problem with scenario one, with starting with that technology, is not only that it can be a very expensive trap for an organization, but see, now we risk taking over the human element. And you know, as technology increases more and becomes more sophisticated in our world, in my opinion and in what I have seen, the human element becomes even more important, and the language of reliability becomes even more important. So it's very important to make sure that the people responsible for our equipment understand why change is taking place. Because if you just, you know, install a sophisticated monitoring device and now, you know, hey, you tell Johnny, you don't have to do that 6-month task anymore. We've got this monitoring device. It can leave people feeling confused. It can leave people feeling left out, maybe even angry is maybe too strong of a word. But that really contributes to the decline in reliability culture. So we can have the best devices and the best systems in place, but if our reliability culture, if our people are not acting as a cohesive team, that in itself can be a cause of chronic failure. So when it comes to CBM, but not just condition-based maintenance, you know, now today, what is on the scene is the industrial Internet of Things, artificial intelligence. We now hear about the digital twin. So really any improvement process is we need to start with the fundamentals and not leave anyone out. And that's one thing, that's one way that RCM can serve in your organization, aside from all the excellent failure management strategies that we can derive from the process, but it can also serve to share the fundamentals with your reliability team so that we start to build that culture and that cohesive team. I'll pause here in case there are any questions. Okay, we'll move on, but just make sure that you can still hear me.
We can hear you.
Okay, perfect. Okay, now I want to debunk a couple of myths right now because I often get asked the question, should we do RCM, should we do CBM, or should we do FMEA, failure modes and effects analysis? But here's the thing. When you do RCM correctly, the first 4 steps make up the FMEA or the FMEA, the failure modes and effects analysis. When we add step 5 to the mix, consequences, that adds criticality. So steps 1 through 5 create or make up the FMECA or the failure modes, effects and criticality analysis. So if you're doing RCM properly, then you're largely satisfying the requirement for an FMEA or a FMECA. And as we just went through, embodied in step 6 is the consideration of condition-based maintenance. So when you do RCM, you're doing FMEA, you're doing FMECA, and you're also considering condition-based maintenance. After we get past step 6, the last step is step 7, and that is default strategies. And embodied in default strategies is also figuring out how we could possibly manage each failure mode, because it may not be about maintenance. When we started talking, when we first opened with the presentation, we talked about how there are other elements that affect the system, like the quality of our emergency procedures, how comprehensive our training procedures are, operational tempo and environment, right? Where we're operating our equipment and how often we are operating it. So it stands to reason that there are other things that we may have to do to take care of our equipment other than maintenance, like maybe update a tech pub, or maybe we've got to redesign something on our equipment. Maybe we need to do a failure finding task, taking care of our safety systems, protective devices, those devices and systems that are intended to keep us safe in the event that something else goes wrong, like fire alarms and pressure safety valves. But we may also say, you know, there are a lot of failure modes in complex equipment that we run to failure. So for a lot of failure modes, we may consciously decide to do no scheduled maintenance. So there are other products from an RCM analysis other than just maintenance. All right, I want to talk about data for a moment because it brings us to a very important facet of how RCM is applied. And I want to talk about historical data and the RCM process. Now, I know baseball is an American thing. When I grew up as a little girl, baseball was very big in my house. I grew up in Boston with the Boston Red Sox. So I want to look at some batting data. Now, just to give you some context, a 198 average in baseball means the person up at bat is getting a hit 2 out of 10 times. That is really bad in baseball. Now, 0.4 is nearly unachievable. The best overall average was 0.366, held by Ty Cobb like decades ago. But the point of me showing you this is this. Let's say we've got player Smith and he's getting a hit every 2 out of 10 times at bat. When we look at this data, we can conclude something very important, and that is player Smith is really bad and he needs help. So if I'm the batting coach, I can use this data to know who I need to work with, who needs help, right? The problem is that the data does not tell us what is specifically causing player Smith to be such a bad player, right? Does he need to change his stance? Does he need to start swinging a little sooner or start swinging a little later? It doesn't tell us what specifically is causing him to be such a poor player. Well, when it comes to historical failure data, most organizations run into the same thing, where the historical data is advantageous. It's helpful in identifying high cost drivers, right? Identifying, you know, where our problem points are, but it seldom gives us the kind of detail we need to come up with solutions. So now we said when we opened the presentation that most failure modes are failing randomly. And if that's the case, and I don't have historical data that I can use to manage every failure mode, where do I get the information I need, right? We've talked about the 7 steps of RCM, and we've gone through we've talked just about a few points of the philosophy with the useful life and the P2f interval. Well, where do we get this information? And what I have seen over and over again, what I have experienced in over 20 years of facilitating RCM analyses, is that a facilitated working group approach to reliability-centered maintenance can be so advantageous for an organization. The equipment experts within an organization, in my experience, are the untapped gold within any organization. You know, the people that have been there for 5, 10, 20, 30 years, where they have all this operating experience. They understand the machine, they understand the environment, they know the nuances when it comes to the machine. So one way to augment the holes in any historical data that you might have is to use a facilitated working group approach to RCM, where you actually gather the equipment experts in a room at the same time. It's the analysis is led by an RCM facilitator, and you've got people who represent the various disciplines for the equipment, like operators and maintainers and engineers, electricians, whoever you might need for a particular analysis. Now, this example shows that there are 7 people on a working group. Depending upon the equipment, there may just be 3 or there may be 5. That certainly could vary. But a facilitated working group approach can produce incredible results. And another byproduct, because we talked about in the beginning where we talked about, yes, you can come out with failure management strategies when you do RCM, but the process can give you so much more, like fostering an effective reliability culture. But another really key thing that it does is this, and I've seen it over and over. When you've got an equipment expert in the room who's been there for 20 or 30 years, the knowledge that they have is insane. Now, when you sit down and you populate an RCM analysis, especially in the first 4 steps with the failure modes and effects analysis, especially when writing failure effects, a detailed story of what would happen if we did nothing to predict or prevent the failure mode, a whole lot of learning goes on when failure effects are written properly. And the people involved in giving the information to write that failure effect are oftentimes these equipment experts who have been there for so long. So it's like a download. It's like a download button where we take their knowledge and their experience and we memorialize it in this analysis. So if they do retire or they move on to maybe a different position, we have now capitalized on that information and we've memorialized it for ourselves. Okay, the last things I want to talk about have to do with RCM implementation. And here is another area where sometimes organizations can make some missteps when they do reliability-centered maintenance, and then, RCM gets a bad rap. People will say, well, we didn't get what we needed from RCM. It took too long. It was too complex. If that happens, it's usually because the process wasn't applied properly and all the right people weren't involved in the process. But here are some key points about implementation. If you are thinking about implementing RCM, I would definitely say you start small. Do 1 or 2 or 3 pilot projects so you can see for yourself what RCM can do, and then implement RCM more broadly. It's not like you have to decide today, well, we're going to do RCM or we're not going to do RCM. Really, it's like anything. Experiment with it in the beginning to see what you can get from it and if it meets your needs. The other thing is that for pilot projects, it's important to choose equipment that's causing the most pain. And whatever that pain is, whether it's chronic failure or maybe it's just increased costs, whatever that pain point is, start with equipment there that's giving you the most trouble. Another thing, and I hear this frequently in our industry, is that you have to decide to be an organization that does RCM or doesn't do RCM. But you do not have to do RCM on all of your assets. You can choose where RCM will be effective. I mean, in fact, depending upon the industry, there could be tens of thousands of individual pieces of equipment. So it's really physically not possible to do full-blown RCM on everything. So really, it's up to you to choose where RCM would be most effective. Another thing I want you to leave knowing is this, is that RCM can be done on any asset. It can be done on electronics, just like it can be done on mechanical equipment. I've facilitated an RCM analysis on a tech manual When I was working with the CH-47, the Army's Chinook helicopter program, this is when electronic technical manuals, when they were first implementing them within CH-47, the electronic tech manuals that they had were awful. They weren't user friendly. All the information they needed wasn't there. So we actually did an RCM analysis on the tech manual and came out with recommendations. Now, obviously, we skipped step 6 because there's no proactive maintenance to be done, but we had a whole lot of other default strategies, recommendations as to how to make the tech, how the tech manuals could give the user what they needed. The last point is don't go it alone, meaning you can't just read a book or watch a quick training course and then implement reliability-centered maintenance. There certainly are nuances that have to be learned for it to be applied correctly. I want to close with what RCM achieves. So obviously, it helps us to achieve reliability goals. We've already talked about how it helps us to foster an effective reliability culture. It can definitely help us enhance worker and environmental safety. And I want to give you one example how, and this is a really simple example. I'm going to show something on the screen really quickly, and then I'm going to take it away. Okay, so what I just showed you are yogurt containers. I love yogurt. In fact, I eat yogurt for dessert every night. And I love lemon meringue yogurt. Well, I went to the store and I bought 8 of these. And I thought I was buying lemon meringue yogurt. So the next day I open up the yogurt and I smelled something. It didn't smell quite right, but I wasn't really paying attention, and I took a spoonful and put it in my mouth, and I realized that I had bought banana cream. Well, I really like fresh bananas, but I can't stand anything like banana bread or banana pudding or banana candy. It's very off-putting to me. So I know that this is just yogurt. Now, it had operational consequences to me because now I've wasted money on 8 tubs of yogurt that I'm not going to eat. And that's not a big deal, right? But consider the equipment that you're responsible for. Equipment that, if it were to fail, could injure or kill someone. So when you look at these two, the reason why I wanted to show you this is that the lemon meringue looks, at first glance, it looks almost identical to the banana cream. Now, this is just yogurt, but what if a valve was mislabeled or was vaguely labeled or was labeled in a way that it would be very easy for an operator to make a mistake and that could potentially have severe consequences? We call these things in our industry latent failures. It's like an accident waiting to happen. And these things happen in our world every day. You can just go online and look at the news, and every day there's another disaster. Certainly no one meant to make happen, but it happened because mistakes are made. But you see, the equipment experts, the teams that we assemble, they know where these improvement opportunities are. They know where these latent failures are. So when we ask them the right questions in a formal environment, they're able to share with us these various issues. We can put them into our analysis so that we can potentially affect some positive change. We certainly can improve equipment performance, eliminate unwanted downtime, make efficient use of our resources, get better product quality. And a really important thing that I've already mentioned is that we document an audit trail for all of our decisions. And another thing is that if there is some sort of a redesign or some sort of a one-off change that has nothing to do with maintenance, it stands a much greater chance of being implemented because in the RCM analysis, We've outlined the consequences. We've outlined what could happen if we don't make the change. So it's formally documented, and it's a way to formally elevate these issues to management. So that is everything that I had prepared to share with you today. Something else my mentor, John Moubrey, taught me is that as human beings, time is our most valuable asset, and you chose to spend your time with me today. And for that, I am sincerely grateful. I would be happy to answer any questions. And if you have any other questions down the road, you can certainly email it, but I'd be happy to answer any questions that you might have now.
Varsågod, Vebjørn.
Yeah, I have a question. There's a kind of a standing debate in our company regarding steps 6 and 7. And I wonder if you can shed some light on it, because in my view, or in some of us's view, the considerations when it comes to what's technically appropriate and worth doing on the tasks, both in 6 and 7, it's on the abstract level, the considerations are the same if you don't look at the failure mode's characteristics. You know, in my view, there's no task that are better than the other in just by you know, generic type of task. I mean, it's all comes down to if it's lowering the risk, if it's worth doing, and etc. So I wonder what if you can shed some light on why it's separated into 2 different steps, the 6th and the 7th step.
Okay, well, okay, so, and let me just show. Okay, so step 6 is when we consider maintenance, right? Proactive maintenance. And step 7 is default strategies. So embodied in step 6 is just scheduled restorations and scheduled replacements. Let me go to that slide. Step 7 is when we consider default strategies. For example, is there like a redesign, or do we need to add an operating procedure? So I'm not sure that answers your question, but maybe this will answer it. If it doesn't, let me know. Because you mentioned the characteristics of a failure mode. That's why it's really important to make sure failure modes are identified correctly, and that we really do manage physical assets at the failure mode level. So you have to take each one on its own and consider what is best. Like, for example, if we just go back to my engine oil, right? That my engine oil has a useful life, 7,500 miles. But just because it has a useful life doesn't mean I couldn't do condition-based maintenance on it. So for one failure mode, there may be multiple maintenance tasks that could be done. So you've got to figure out which ones are technically, like you said, technically the right thing to do, and which ones are worth doing. Maybe doing oil analysis would be cheaper than doing a scheduled replacement every 7,500 miles. So your mindset is correct in that you're thinking at the failure mode level. But what a lot of people think is, I just gave a training course last week, and there was, before we got into the details of RCM, the maintenance manager was frustrated about some generators that they're having problems with, and he said, I need to know how often I have to maintain my generator. Well, that's an impossible question to answer, because you have to break it down to the failure mode level to figure out how often or what you need to do for each individual failure mode. So that's where we get back to a proper reliability culture, where people need to be thinking in terms of failure modes and not like, oh my gosh, what do I do to the generator? I'm not sure I answered your question though. What are your thoughts about that?
Well, yeah, kind of, but I think my question is more related to, isn't there in some cases more beneficial to do default actions than do maintenance tasks, and why is default actions by standard considered just after you have considered maintenance tasks first? Like, what couldn't it be the opposite way as well? In certain, couldn't default actions be more appropriate and more worth doing in certain cases?
Yes, it absolutely could be more worth doing. But the reason that we consider proactive maintenance before default strategies is because if there is a proactive task that we can do, then we can manage that failure before the failure occurs. So with default strategies like no scheduled maintenance or like failure finding, for example, testing a fire alarm system every year, the reason we always want to consider proactive maintenance first is because it's proactive. So if we're testing the fire alarm every year, then we are essentially accepting the fact that it could spend some time in a failed state. So when you look at the RCM algorithm, that's why a default strategy is considered after proactive maintenance.
Yes, well, now we are on overtime, but we have 3 more questions, and I ask you please to make these questions short. And then it's first Paul Øyri, then Håvard Hansen, and then Yngve Rune Olsen. And then we have to draw a line, I think.
Okay, I'll try to be short. Have you seen the Norsk Z008 procedure? It's called risk-based maintenance and consequence classification. Because in my view, FMEA is covered in the maintenance concept, while the consequence classification require much more management and production people to decide. It's not right to have electricians to decide the consequence of an electric power. So just your viewpoint on that.
Okay, so my viewpoint on that is this. So when you assemble the team of equipment experts, they allow a failure effect to be written properly in the right amount of detail. So the whole point of writing a failure effect is so that you can assess consequences. Now, in my experience, most failure modes, consequences can be assessed really just using technical common sense. If we talk about risk-based maintenance, you know, there are some failure modes that maybe could potentially be so severe that you may want a formal risk analysis done on them, but there are far more failure modes where it's often appropriate just to assign, you know, safety, environmental, operational, non-operational, and to know that a particular task will adequately manage it. So it's really not the electrician who is assessing the consequence. It's for example, an electrician on a working group gives his knowledge and information so that a failure effect can be properly written so that consequences can be assessed properly.
Okay. Yeah, well, I agree with you. It was wonderful. Good presentation on the
Thank you.
basics.
Now Håvard Hansen has time for a short question. We don't hear you. I'm sorry.
Can you hear me?
Yes.
Good. My name is Håvard Hansen. I want first of all to thank you for a very interesting session. I think that RCM is the best way to establish a PM program if you realize that it's more than listing tasks from the vendor, you know. But the strange thing is that, at least in Norway, it's not known, you know, by maintenance managers. Do you have any thoughts about why?
You know, here's why here's why I think is why. And it's not just Norway. And if I have to just be totally honest, I talk to so many people every week who, like a P2f interval, the P2f curve, I will share that with them, and then they think I'm some sort of a genius, which I am not. This, you know, this concept is 40 or 50 years old, but yet people still don't know about it. RCM principles are over 50 years old, but most organizations still don't use RCM or use the principles embodied in it. And I think the biggest reason is because it takes work. You know, reliability-centered maintenance takes time and it takes resources. When it's done properly, it can be done relatively quickly and efficiently, but it's all relative, right? I mean, you can't do an RCM analysis on one big system in a day. And I think it is because it takes that commitment and it takes that work that people don't use it, and it's not widely known. Another reason is I think a lot of organizations out there are in reactive mode. They're running around from fire to fire. So it's very hard to get out of that mode and get proactive. And if you just think about it from this point, let's say you needed to lose 50 pounds. Well, losing 50 pounds is simple, but it is not easy. You have to be dedicated, you have to be committed, and you have to use your will every single day not to eat junk food. It's not easy, but it can be done. It's the same when it comes to reliability-centered maintenance. That's why I think, but it's not just Norway. It's absolutely the way in organizations all over.
Then Yngve Rune Olsen.
Yes, hello. I'm Yngve Rune Olsen from Bilfinger. We are one of the larger service companies for maintenance in Europe and also North America. And RCM, I think, is, as Håvard mentioned, actually, funny enough, not very well known. I think it is known, but there is a fear that it's very time consuming, and maybe you have heard about projects for running from years and are not finishing. So the management is maybe afraid of starting something that will cost a lot of money. So I think it was, I will salute you on your statement that you can do RCM on one asset. You can choose which assets. You don't need to take everything. I think that was a very good message that you sent today also.
Thank you. If I could just add a couple of quick things. So there are several reasons, but two main reasons why if an RCM analysis is not done well, or it just like goes on and on and on, and it becomes this enormous analysis. Number one, if functions aren't written properly, when we do RCM generally to produce a maintenance plan and other default strategies, we produce a functional FMEA, not a design FMEA, not at the component level. We don't write functions for every nut and bolt and resistor. We write what we need the equipment to do. So it limits the number of functions. But what often happens when people are inexperienced with RCM is they write functions that don't matter. The other thing is failure modes, either writing failure modes way too generically or writing way too many and getting way into the weeds where you end up with 1,000 failure modes, which would be ridiculous for an analysis. So that's why it's important to make sure you know how to do RCM properly. And I'll just add one final thing. Not only can you just not do RCM on one asset, but let's say you have a major air compressor and you're having big problems within the lubrication system, you could just do an RCM analysis on the lubrication system. You don't even have to do it on the whole compressor. So yeah, it all comes back to making sure that you do it properly. You know, RCM is common sense applied to physical assets. But if you don't know the language and you don't understand the techniques, you can really get into some serious rabbit holes and waste a whole lot of time.
Thank you.
Sverre?
Yes, thank you. Yes, thank you. Thank you very much, Nancy. This was, as I knew, a very good, clear presentation, and you made all the right emphasis on all the important challenges and the details in the method. I'm very happy for this. I just want to make one comment to Håvard Hansen's comment again. And I think we tried RCM in Norway for about 30 years completely in a lot of industries. But I think the key that Nancy mentioned before is that you can read John Moubrey, you can read Nolan and Heap, you can read Nancy's book, and that gives you a very good understanding of what this is. But you need to train the facilitators, and you need to have a very structured process through the RCM 7 questions and everything. And this is a very good document trail on what you do and decide and know about your equipment. And this will again help you to evaluate and improve your maintenance program in the analysis methods during the maintenance work has done. So implement this into your, in Norway called vedlikehold, is a very good key part. I train my people, my facilitators. I certify my RCM facilitators to make sure that we are on the to the point and do the RCM most efficient and focus on the key points. So and I had a lot of discussions with Nancy, and this helps me a lot. So thank you again, Nancy. I think you gave a good presentation. I think this was very good, and I think a lot of people got some more power to continue the good RCM work that I know a lot of you guys out there are doing. So thank you again, Nancy.
Excellent.
Yes.
Thank you. Thank you very much.
Thank you, Nancy, and many thanks to everyone who participated. We will make Nancy's presentation available to you on my page, as I said earlier. And I'm delighted to tell you that we are in process and are hoping to be able to offer you a course with Nancy later. You will also find information about all our other courses on nfv.no or qualitynorway.no. And if there is something you need help with, do not hesitate to get in touch. Have a nice day, and thank you again to Nancy for getting up so early in the night. Yes.
It was my pleasure. Thank you.
Yeah, thank you from me as well.
Thank you. You're welcome. It was my pleasure. Thank you so much.
Yep.
All right. Bye-bye, everyone.
Bye-bye.
Bye-bye.